All right, the next topic what we're looking at is energy and the conservation of energy. And I think I can say without hyperbole that this is the most important organizing principle in all of science. And it's basically this: energy can't be created or destroyed, it can just be changed from one form to another. This is another way to look at the world, and it's a really, really great one because anything that happens involves a change in energy from one form to another. So thinking about things in energy terms will apply to literally anything. And this is a law of physics. Okay, conservation of momentum really wasn't at the level we consider it, but conservation of energy is. And it turns out energy comes in a dizzying variety of forms. You can freely convert them one to the other, but you can't create it and you can't destroy it. But before I do that, I want to do another installment of things I like about your generation. And one of the things that I really like about your generation is your curiosity. Okay? I'm very, very impressed by the kinds of things that people will say to me. People come up and ask me amazing questions, and they'll share interesting insights and ideas with me. And you folks kind of get that the world is a fascinating and interesting place, and you're studying science not just as a tool to get a good job someday, but as a tool to satiate your curiosity, to learn more about the world. And I really, really appreciate that about you folks. Now, energy, as I've said, this energy formalism is another way to look at the world. And one of the things I want to do in this course is I want to show you different ways to look at the world. And one way is to use this energy formalism. Energy can be transformed from one form to another, okay? And when that happens, that transforming energy from one form to another is always involved in anything that happens. Anything that happens involves a transform of energy from one form to another. And so understanding the world means understanding how and why energy changes from one form to another. This is absolutely true. Now, in the book, you can look at, and this is chapter 10, and I want you to take a look at chapter 10. Energy comes in a variety of different forms. There's kinetic, gravitational potential, spring potential, thermal energy. We've got chemical energy, nuclear energy. We won't talk about those so much, but these four right here, we will spend a lot of time thinking about these particular ones. We'll solve a bunch of mechanical kinds of problems with them. And we have this basic energy model that we're going to use that works like this. We are again going to be concerned with systems. So we'll take the universe and shrink it down to some subset that we're going to consider. And inside that system, you can freely convert kinetic energy to potential. You can freely convert kinetic energy to chemical energy. You can freely convert chemical energy to potential energy. And these are all reversible transformations. They are two-sided arrows that go one way or the other. Or energy can be converted to thermal energy. That's a one-sided arrow. Once it goes that way, it doesn't go back. And so we can basically just consider the total sum of energy in the system and say that it's equal to zero. Now, one other thing that can happen is you can have work. If work comes in from the outside, that changes the store of energy that you have in the system. Now, thermal energy is special. When you convert energy to thermal energy, it doesn't go back. Okay, when you burn logs on the fire, the gases don't recombine and spontaneously make a log. They do in a tree, but that requires the input of solar energy. When a shooting star comes in, its moving kinetic energy turns into thermal energy, which is why I get the glowing kind of like line in the sky, but it doesn't go backwards. In principle, the atmosphere could get really hot, so it has high thermal energy, and then it could grab a pebble from the earth and hurl it into outer space. You could reverse this process. It doesn't happen. When you transform energy to thermal energy, that is irreversible. It doesn't go back, and that's worth noting, and we'll have more to say about that when we get to chapter 12. Now, in this course, one of the things that people ask me, and I've told you not to do this, people often say this: which equation do I use? And if you're asking that question, you are asking the wrong question. Because if you've identified what sort of problem that you're looking at, the equation that you use should suggest itself. And if you have determined that a problem is best solved by using the ideas of conservation of energy, which equation do you use? This one. This is the one equation that we use for every single conservation of energy problem that we do, okay? Now just note, there's a work term in here. Work can be positive or negative. We're ignoring heat for right now, and thermal energy is special, so remember those things. But take a look at this equation. This equation basically says the initial energy I have in a system plus the energy I put in is equal to the final energy that I have in a system. And I'm going to say the change in thermal energy because it can only increase, it can't decrease. And so we're going to put it over on that right side of the equation. Every single problem we solve will solve this way. And I'll show you the kind of problems we're going to solve. We start, as with conservation of momentum, by looking at before and after pictures. Consider the situation before, consider the situation after. That's going to be crucial. So here's an example. I used to have this little yellow Datsun. His name was Emoto of the Bushveld. Long story there. Anyway, when I lived in Swaziland, and it was pretty dilapidated, but it got us from point A to point B. It got us to a lot of amazing point Bs, actually. But it would only start if you got it up to speed and then popped the clutch. And I had to get it up to about 4.5 meters per second in order to make it go. So what I would do is I would just park on a hill, and then I would get in the car and I would stick my foot out the door and I would give it a little bit of a shove and start rolling down the hill. And I got going fast enough, I would pop the clutch. And that was fine because Swaziland was a really, really hilly country. So the question is, if I'm going to do this, what is the minimum possible height hill that would do the trick? First off, I'm going to treat this, I'm going to do some strategizing. And for the strategy, I'm going to say, I'm going to treat this as a conservation of energy problem. I'm going to treat it as a conservation of energy problem, okay? And to do that, I have to have a system. And the system can be one object or two objects or multiples. But in this case, the system I'm looking at is just the Datsun. It's just the Datsun. That is my system. And the next step is to prepare. And the preparation step looks like this. I'm going to draw a before and after visual overview, and you've seen that in chapter 10. And again, it's crucial to draw these pictures. So the situation looks like this. Here's my before, here's my after. The car starts, oh, and it was yellow dots, and so I'm going to draw a yellow car here. It was a yellow car at the top of the hill, not moving, and my final state was a car in motion at the bottom of the hill, and I want it to be moving at 4.5 meters per second. Okay, because that's the slowest it could be moving. And the question asks, what was the minimum height of the hill that would allow this to happen? Okay, what is the minimum height of the hill? Now, I'm going to identify some heights here. I'm going to say my initial height, my final vertical position is equal to 0. My initial vertical position is just going to be equal to h, the height of the hill. Okay, I can say that. And then I also want to think about what is the energy transformation that takes place. And it looks like the energy transformation that takes place, the car starts at a high point, not moving, finishes at a low point, in motion. This looks like a conversion from gravitational potential energy to kinetic energy. Okay, and then how do we solve this problem? The way we solve it is this. We're going to do our one equation, and our one equation was the initial kinetic energy plus the initial potential energy plus any work that's done is equal to the final kinetic energy plus the final potential energy plus any change in thermal energy. And let's think about these terms in turn. Well, the work is this: did someone push? And if someone pushed, that's something that's external to the system that is putting energy in. But in fact, nobody pushed. I could get people to push the car. In fact, I did on many an occasion, but in this particular case, we're not considering that. Thermal energy is like lost energy to thermal energy, and that would happen, for instance, if you put on the brakes. But if I wouldn't be putting on the brakes because my goal is to get the car up to speed. Let's assume there's no friction, no losses, and so we got that. Let's look at the final potential energy. Well, the car is at a height of 0 at the end, so no gravitational potential energy at the end. And now let's think about the kinetic energy. Kinetic energy is 1/2 mv squared. The initial kinetic energy is 0. And so my situation reduces to this. The initial potential energy is equal to the final kinetic energy. Now, you compute potential energy using the expression m times g times y. So that's just m times g times h. That's my initial potential energy, where h is the height of the hill. My final potential kinetic energy is 1/2 mv squared. And let's see what we can put in here. Oh gosh, something awesome happens here. Mass goes away. That is handy because we weren't given the mass of the car, and that's something we've seen before. We know the height of the hill. Actually, we don't know the height of the hill. We're looking for that. I know the final speed is 4.5 meters per second. And with that in hand, the only thing I don't know in that expression is height, and I can solve for it. And if I take that equation and solve it for the height, I get a height of 1.0 meters. Okay? Next piece of the puzzle, assess. And here's how I assess this. I used to put it at a hill outside my house, and by the time I got to Rachel McGinn's house, I was at about the right speed, and I would be able to get it started, and the amount I dropped was probably just about 1 meter, is what I would estimate. And so my assessment is that, in fact, this matches my experience of the world, as it should. Now let's take a look at another problem that we could solve, and here's one involving a classic coaster. So at the bottom of the first hill, the coaster has reached a speed of 24 meters per second. Now heads up a hill and it rises 12 meters from the dip. Question, how fast is the coaster moving at the top of this hill? How do we start? We strategize. And we're going to strategize by saying, I'm going to treat this as a C of E problem, conservation of energy. And the next piece of the puzzle is I have to consider the system. And the system is just going to be the coaster, because the coaster is moving, and as it's going up and down, it's converting potential energy to kinetic energy. And in fact, that's all a roller coaster does. The whole ride, you're just converting potential energy to kinetic energy and kinetic energy to potential back and forth. Next piece of the puzzle, prepare. And for our preparation step, we're going to draw a picture. So at the bottom of the first hill, the coaster is moving, and then it comes to the top of the hill. So it starts out down here, and it's moving at a speed of 24 meters per second. And then it rises to the top of a hill. And we want to know what is the speed that it's moving at up here. VF, we're looking for VF, and we don't know. And we're told that it rises 12 meters. So I'm going to set the 0 of my height to be right here. I'm going to say where the coaster starts out, that's going to be a height of 0. And then the final height is going to be 12 meters, because it's 12 meters above where it started, so YF is equal to 12 meters. So I have my initial height, I have my final height, I have my initial speed, I don't have my final speed. We have everything set up and ready to go. And now we're ready to solve, and we solve by using our basic expression Ki plus Ui plus W is equal to Kf plus UF plus delta E thermal. Now, let's think about the terms in here. First off, there's not going to be any work. Okay, that's because nobody is pushing. It's a roller coaster. Okay, and the fact that it's coasting means nobody's pushing. So coasting, no work. Also, it's rolling. Rolling is very low friction, so we assume there's no delta E thermal. So those two terms go out. Another thing we can cancel is the initial potential energy, because we assume that it started at y equals 0, so no initial potential energy, but all the other terms still exist. So our equation reduces to Ki equals Kf plus Uf. Okay, and the initial kinetic energy was 1/2 times the mass of the coaster times 24 meters per second squared. The final kinetic energy was 1/2 times m times Vf squared, which I don't know what Vf is. And our final potential energy was 1/2 times, it was just m times g times the height, but the height that it rises to is equal to 12 meters. So if you look at this expression, I know everything in this expression except for Vf, and so I can take this expression, solve for Vf, and if I do that, I get Vf is equal to 18 meters per second. Okay? Final piece of the puzzle, to assess 18 meters per second at the top of that second hill. You're still moving really, really fast. And actually, this is data that is I think I got this data for the Twister 2 at Elitch Gardens, which I think this is a picture of. And That sounds about right to me, because at the bottom of the first hill, you're moving very, very fast. And at the top of the second hill, you're still moving pretty fast. So my assessment is, yeah, this kind of matches my experience of the way the world works. Next, we're going to talk about energy and biological systems. And when we do that, we have to consider the question of efficiency. So when you're actually using energy to do things, and we're going to be particularly concerned with biological systems, we need to be consider questions of efficiency. And our animal we're considering in this case, we're going to talk about kangaroos, but also sloths, which are just breathtakingly efficient for different kinds of reasons, as we will talk about when we turn to that topic.